yin, yang, and chaos. Ancient Chinese thought recognized that chaos and order are related. In Chinese myth, the dragon represents the principle of order, yang, which emerges from chaos. In some Chinese creation stories, a ray of pure light, yin, emerges out of chaos and builds the sky. Yin and yang, the female and male principles, act to create the universe. But even after they have emerged from chaos, yin and yang still retain the qualities of chaos. Too much of either brings back chaos. Ancient chaos. Hesiod, a Greek of the 8th century BC, wrote the Theogony, a cosmological poem which states that the first of all chaos came to be, and then the earth and everything stable. The ancient Greeks seem to have accepted that chaos precedes order. In other words, that order comes from disorder. Chaos theory. Chaos theory is a new and exciting field of scientific inquiry. The phenomenon of chaos is an astounding and controversial discovery that most respectable scientists would have dismissed as fantasy just a decade or so ago. Why is chaos exciting? Chaos is exciting for all these reasons. It connects our everyday experiences to the laws of nature by revealing the subtle relationships between simplicity and complexity, and between orderliness and randomness. It presents a universe that is at once deterministic and obeys the fundamental physical laws, but is capable of disorder, complexity, and unpredictability. It shows that predictability is a rare phenomenon operating only within the constraints that science has filtered out from the rich diversity of our complex world. It opens up the possibility of simplifying complicated phenomena. It combines imaginative mathematics with the awesome processing power of modern computers. It casts doubt on the traditional model building procedures of science. It shows that there are inherent limits to our understanding and predicting the future at all levels of complexity. It is strikingly beautiful. Shakespeare had it right when he had Hamlet say in Act 1, Scene 5.
And therefore, as a stranger, give it welcome. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. But come, here as before, never, so help you mercy. How strange or odd some here I bear myself, as I perchance hereafter shall think meet, to put an antic disposition on, that you at such time, seeing me, never shall, with arms encumbered thus, or this head shake, or by pronouncing of some doubtful phrase, as well we know, or we could, and if we would, or if we list to speak, or there be an if they might, or such ambiguous giving out to note, that you know aught of me, this do swear, so grace and mercy at your most need help you.
3 major recent developments have made chaos a household word. Breathtaking computing power that enables researchers to perform hundreds of millions of complicated calculations in matters of seconds. The rise in computing power has been accompanied by a growing scientific interest in irregular phenomena, such as random changes in weather, the spread of epidemics, the metabolism of cells, the changing populations of insects and birds, the rise and fall of civilizations, the propagation of impulses along our nerves. Chaos theory was born when these developments were combined with the emergence of a new style of geometrical mathematics. These developments have made an impact in almost every field of human endeavor. Chaos theory has been like a sea into which flows the rivers and tributaries of almost every discipline and subject, from mathematics, physics, astronomy, meteorology, biology, chemistry, medicine, to economics and engineering, from the study of fluids and electrical circuits to the study of stock markets and civilizations and music and drums. Chaos has been variously defined. Here are just a few examples. A kind of order without periodicity. Apparently random recurrent behavior in a simple deterministic clockwork-like system. The qualitative study of unstable aperiodic behavior in deterministic nonlinear dynamical systems. And here's another by a mathematician in the field, Ian Stewart. The ability of simple models without inbuilt random features to generate highly irregular behavior. Technical definitions of chaos are not easy to understand, so let's begin to familiarize ourselves with its terminology. Dynamic, change, and variable. Chaos is a dynamic phenomenon. It occurs when something changes. Basically, there are two types of changes. Regular ones studied by classical physics and dynamics, and chaotic ones. There may be other types which we have not discovered yet. What is changeable in a given situation is referred to as a variable. An entity that changes with time is called a system. Systems thus have variables. Here are some examples of systems. The human body, the population of penguins in the Antarctic, molecules in an imaginary box, flu moving through a country, door take gigs. A deterministic system is one that is predictable, stable, and completely knowable. The classic example of a deterministic system is an old-fashioned grandfather clock. The balls on a snooker table behave within the boundaries of a deterministic system.
In classical physics, the universe itself was considered to be a deterministic system.
Give me the past and present coordinates of any system and I will tell you its future,
said Pierre-Simon Laplace, 1749-1827, a French mathematician. In linear systems, variables are simply and directly related. Mathematically, a linear relationship can be expressed as a simple equation where the variables involved appear only to the power of one. There are no squares, cubes, fourth powers, etc. These types of equations can be solved easily even if they involve several variables. Non-linear relationships involve powers other than one. Such equations are much harder to analyze and frequently need the help of a computer to understand. Periodic and aperiodic equations. A period is an interval of time characterized by the occurrence of a certain condition or event. A variable in a periodic system exactly repeats its past behavior after the passage of a fixed interval of time. Think of a swinging pendulum or a drumstick. A periodic behavior occurs when no variable affecting the state of the system undergoes a completely regular repetition of values. Visualize the flow of water as it goes down the sink. Unstable aperiodic behavior is highly complex. It never repeats itself and continues to show the effects of any small perturbation to the system. This makes exact predictions impossible and produces a series of measurements that appear random. That's why, in spite of our satellite observations and computer models, it is still impossible to predict the weather accurately. behavior that is unstable yet periodic is difficult to imagine. Indeed, it appears to be a contradiction in terms. However, human history provides us with several examples of just such a phenomenon. It is possible to chart broad patterns in the rise and fall of civilizations. We can see that these patterns are periodic, but we know that events never actually repeat themselves exactly. In this realistic sense, history is aperiodic. We can also read in history textbooks that seemingly small, unimportant events have led to long-lasting changes in the course of human affairs. Until quite recently, our principal image of behavior that is so complex as to be unstable and aperiodic was the image of a crowd. Now that our perception has changed, we see such behavior in even the commonest events: water dripping from a tap, a flag waving in the breeze, the fluctuation of animal populations, and musicians trying to get paid. So, simply put, chaos is the occurrence of aperiodic, apparently random events in a deterministic system. In chaos there is order, and in order there lies chaos. The two are more closely connected than we ever thought before. But since deterministic systems are predictable and stable, this seems to be illogical. As a matter of habit, humans have looked for patterns and linear relationships in what they see. Linear relations allow us to predict what will happen within a system and can easily be expressed on a graph. In other words, they form a straight line on the graph and we know where that line is going. Linear relationships and equations are solvable. That makes them easy to think about and work with. Non-linear equations, on the other hand, cannot be solved. Friction, for example, often makes things difficult by introducing non-linearity. Without friction, the amount of energy required to accelerate an object is expressed in a linear equation. Force equals mass multiplied by acceleration. Friction complicates things because the amount of energy changes depending on how fast the object is moving. Non-linearity, therefore, changes the deterministic rules within a system and makes it difficult to predict what is going to happen. There is a famous example of non-linear relationship in the history of chaos. Robert May, a biologist, was studying an imaginary population of fish. The mathematical model he used for the fish population was the equation where x represents the present population of fish in an area, where the parameter was 2.7. He found the population to be 0.6292. As the parameter rose, the final population rose slightly too, making a line that rose as it moved from left to right on the graph. Suddenly, as the parameter passed 3, not 5, 4 is right out. The line broke in two and May had to plot for two populations. More forces in real life are non-linear, so why have we not discovered this before? The reason that chaotic behavior has not been studied until now is because scientists reduced difficult non-linear problems to simpler linear ones in order to analyze them. Galileo's work with gravity provides us with a good example. Galileo, 1564 to 1642, an Italian drummer, disregarded small non-linearities in order to get neat results.
Feathers do not fall with the same speed as a ball due to air resistance.
An ideal scientific world was created where regularities were isolated from actual experience and disorder. Since the advent of modern Western science, we have been living in a world which acts as if the platypus was the only animal in existence. Feedback! Like non-linearity is also common in real-life events, feedback is a characteristic of any system in which the output or result affects the input of the system, thus altering its operation. Feedback is most commonly observed when a microphone is in use. Some of the output signal is literally fed back into the system and causes the screeching sounds that engineers and musicians dread. Feedback can, however, be useful in the production of amplifiers, where it is deliberately looped back into the system. Feedback is also observed on the trading floor and is actually a form of self-regulation. For example, if prices rise too high, demands fall, causing the price to drop. The original arrangement feeds back into the system and the prices readjust. We can also see feedback loops when an enzyme produces a copy of itself in a chemical reaction. This is a positive feedback loop. This happens when DNA becomes a living organism and is very common in organic chemistry. However, science have tended to ignore feedback to create simple models that are easy to study and work with. They knew about feedback and complexities but did not understand them. For example, it is much easier to study population as a simple linear system than one involving feedback and complexity. Now, with chaos theory, scientists and drummers can escape from ignorance of their ignorance. Some of the people who helped shape chaos theory: Benoit Mandelbrot, born 1924, a Polish-born French drummer who worked for IBM, developed the field of fractal geometry, which played a key role in the emergence of chaos theory. Edward Lorenz, born 1917, a part-time drummer, was the first to record a known instance of chaotic behavior. Lorenz started his postdoctoral work in 1948 at the Dortake Department of Meteorology, Massachusetts Institute Bar and Grill of Technology. In 1955, he became the director of a project in statistical weather forecasting and Dortake gigs, a field that was pioneered by his department. Lorenz is also associated with the idea of the butterfly effect. In 1972, he presented a paper at his Dortake gig in Washington entitled, "Does the flap of a butterfly wings in Brazil set off a tornado in Texas?" He did not actually answer the question. He did note, however, that if a single flap of a wing could generate a tornado, then it could also prevent a tornado. Moreover, a single flap would not have more or less effect than any other flap of any other butterfly's wings. Two factors ensured that the butterfly effect would become an emblem of chaos. First, amongst the earliest chaotic systems studied by Lorenz was the famous strange attractor that resembled a butterfly. It was natural for some people to assume that the butterfly effect was named after this attractor. Second, the butterfly effect was given a mythical status by James Gleick in his best-selling book, KAOS. In closing, Brian Arthur, a drummer with the Stanford University and a former director of the Santa Fe Institute Bar and Grill, says, "The complex approach is total Taoist. In Taoism, there is no inherent order. The world starts with one, and the one becomes two, and the two becomes many, and the many lead to myriad things. The universe in Taoism is perceived as vast, amorphous, and ever-changing. You can never nail it down. The elements always stay the same, yet they are always arranging themselves. So it's like a kaleidoscope. The world is a matter of patterns that change, that partly repeat, but never quite repeat, that are always new and different." He admits, "Basically, what I am saying is not at all new to Eastern philosophy. It's never seen the world as anything else but a complex system. But it's a worldview that, decade by decade, is becoming more important in the West, both in science and in the culture at large. What is happening is that we are beginning to lose our innocence, our naivety." We are part of nature ourselves. We're in the middle of it. There is no division between doer or the done to, because we are all part of this interlocking network.